Alright, this is problem 4.65. Complete the following acid-base reactions with balanced molecular, total ionic, and net ionic equations. We have two reactions that we are discussing, again, both described in words so that you can practice writing the equations, the chemical formulas yourself. Part A tells us that potassium hydroxide is going to react with something called hydrobromic acid. We need to come up with the formulas for this. Good practice. Potassium, of course, is K, likes to form +1 ions. Hydroxide is one of those polyatomic ions. It's a key polyatomic ion. It is OH minus 1. So if I'm going to pair those up, they can do so in a 1-to-1 ratio. And I've got some aqueous potassium hydroxide. I can combine that with my hydrobromic acid. Hopefully you're becoming more and more familiar with the list of the strong acids, and you realize that hydrobromic acid is on that list. It is HBr aqueous. Okay, so I've got a strong acid with a strong base. I am going to react them, and as we recently learned, acid-base reactions of this particular type, strong acid, strong base, form water, H2O liquid, and they form a salt. This is nothing more than a double displacement reaction with acids and bases. The ions switch partners. The H plus pairs up with the OH minus to make water. The K pairs up with the Br to make the salt. So here that salt is potassium bromide. That would also be an aqueous ion since it's soluble. This is our overall molecular reaction. Now it also wants us to write these ionic reactions, a total ionic reaction, and then the net. So this is our overall, or molecular, I think they call it. Let's talk about our total ionic, or complete ionic equation, and what would that look like? The total ionic equation, what characterizes that is all ions are existing as ions if they do so in solution. So if I have a strong acid such as HBr, that dissociates or breaks up completely to strong electrolyte. So I've got these ions, both being aqueous, floating around in solution. Likewise, for a strong base like KOH, I've got ions floating around in solution, not necessarily this formula unit. So I've got aqueous ions, okay? Now on the right side, slightly different situation for water because it's a covalently bound substance. It's not a strong electrolyte, as it turns out. So as a consequence, these guys are going to stick together. It's just a characteristic of the compound. If it's a strong electrolyte, the ions break apart and they're shown in the total ionic equation. But if you got a covalent compound that's not a strong electrolyte, you pair up the things, okay? So that's going to stay the same. But this KBr, that's going to exist as ions because KBr is a strong electrolyte. Okay, potassium bromide is a strong electrolyte. So that's our total ionic. Now, remember our net ionic equation? That's where we just show the action. All the spectator ions are eliminated. So as I look at this, I say, okay, bromide and potassium, you appear to be spectators. You do not change. But where the action is, where this neutralization reaction, is H plus combined with hydroxide to make our good friend water, H2O liquid. That's my net ionic equation. That's where the chemical changes for this particular reaction. Let's try our hand then at part B to 4.65. Here we're having ammonia. We're reacting with hydrochloric acid. This is a little bit different reaction, but don't need to scare you, okay? Now, of these two, probably the easier one to write the formula for you at this point might be HCl, hydrochloric acid. Hopefully you recognize that by now as one of your strong laboratory acids, a very common strong acid. Now the one that might be a little bit harder for you is ammonia. Now, the formula for ammonia, you probably have heard of it before, but the formula is NH3. That's ammonia's formula, just by definition, okay? One nitrogen bonded to 3 hydrogens. Now you look at this reaction at first, and you might be a little bit confused because above, this is sort of our characteristic strong acid, strong base reaction where you've got some acid with an H plus and some base with an OH minus. It's okay, H plus and OH minus, I understand how they can come together to make water, and that makes a lot of sense to me. But part B is also an acid-base reaction. It's just that the substances fall under different definitions of acids and really bases in this case. Ammonia, as it turns out, is going to be our base. And HCl is always going to be an acid, okay? By this alternate definition of acids and bases, which is called the Bronsted-Lowry definition, you'll learn more about that also in general chemistry 2. It's a major topic in general chemistry 2. But a base, by this other definition, is a substance that accepts protons. So it turns out that for this reaction, what happens is this proton, this H+, is accepted by the ammonia to make this polyatomic ion. Now this is on our list of polyatomic ions. This is called ammonium with an I-U-M ending. Ammonium. This is ammonia. This one does not have the same name. It's ammonium with the I-U-M ending, right? Now so the proton is transferred to NH3 to make the NH4 plus. Oh, and whatever left comes along for the ride. Here that's the counter ion, or the Cl minus. This is also an acid-base reaction, okay? Now, I used some lingo there, and I want you to think about it for a second. I said that the acid's proton was transferred, right? Acids are proton donators in the Bronsted-Lowry definition, and bases are proton acceptors. So what do we mean by protons? I mean, we've learned protons are these subatomic particles present in the nucleus, but they're usually off limits for chemistry. Like, what does this involve, okay? What I want you to think about for a second is H+. When I say proton, that's what I'm talking about, okay? H+. This is a hydrogen atom. It's an ion. How many protons does hydrogen have? It's just one, right? Typically. Well, always one. I was thinking about neutrons for a second. So always one proton. Now if it's neutral, it's got an electron as well. But if I make a +1 ion, I've stolen that electron, put it somewhere else. So what's left? Just a proton, right? So when I say proton, that's kind of what I'm talking about in H+. Okay? So it's typical kind of chemistry lingo. It turns out also, just for the record, that this H+, a proton donated from an acid, really truly never exists in this form in aqueous solution. Instead, it actually exists as H3O+. This is called the hydronium ion. It involves a proton being picked up by a water molecule to make H3O+, hydronium ion. So this is how it's believed to exist in aqueous solution. Nonetheless, sometimes this terminology gets thrown around. Protons are transferred, okay? That's kind of what we mean by it, all right? In any event, this is an acid-base reaction. We have a proton donator, a proton acceptor to form the products, okay? This is our overall reaction. Now, if I'm going to write a total ionic reaction, I again write all my species that exist as ions. So for HCl, since it's a strong electron, a strong acid, I'd write H+ plus Cl minus, because when you put this into solution, these ions are separated. They're floating around separately from one another. However, NH3, my ammonia, is a molecular compound, so that stays together. There's not really any charge there. It just kind of comes along floating in solution, okay? I'm going to make my NH4 plus my ammonium, and I'm also going to make my Cl minus as a result of this reaction. Okay, so anything that doesn't change is a spectator. I'm getting ahead of myself here, but I'm already thinking about writing my net ionic, right? Remember that net ionic is that bare bones description of the change. So what is the same on both sides? What's a spectator? It looks like chloride is. So I'm going to cancel that out. And my net ionic is H+ plus NH3 to make my NH4+. So acid-base reactions, overall equations, total ionic and net ionic equations. Hopefully you're getting more familiar with these equations by this point and what they involve, spectators, etc., etc. In terms of writing equations and predicting products for this, if you got the strong acid, strong base, you make water and a salt. Okay, that's pretty straightforward. What these ions are may change a little bit, but usually you've got H plus and OH minus, and that's what makes your water. Now the second category of reaction, it's a little bit, I think, more confusing because you have to think about acids and bases in different terms. Acids are substances that donate H plus. Bases are substances that accept the H plus. So they're a little bit different definitions. And it takes a little bit more practice for you to be able to write the correct chemical equations. But with a little bit of practice, I think that you can get it. And I encourage you to keep taking a look at that until you become an expert.